Well, good afternoon, everybody, and welcome to the USC Viterbi School of Engineering Faculty Roundtable with the faculty of the Astronautical Engineering Department. My name is Paul Ledesma. I'm the Executive Director of Undergraduate Admission here at the Viterbi School of Engineering. I will act as your host for today as we get through this next hour exploring everything and anything under the sun related to astronautical engineering. I guess under the sun, around the sun, everything, near, far from the sun. It's
Yeah.
not just under the sun at this point. I just realized this is the one department that is not under the sun. It's beyond the sun. It's everything. So what we're going to do, I don't want you to hear a lot from me. I want to make sure that you start to get to know everyone that's here with us. I'm going to have each of our faculty introduce themselves, and then I will act as your host that will guide you through some questions and discussion that we get into this process. But first, without further ado, we'll start with our professor and chair of the department, Dan Erwin. Dan?
Thanks, Paul. Hi, everybody. Welcome. I'm Dan Erwin. I'm the professor and chair of the Astro Department. I was actually one of the founders. We just celebrated our 20-year anniversary. Um, so uh, I was an undergrad at Caltech. I was actually in grad school here at USC. I got my PhD here in electrical engineering, and uh, in the 1990s, we got a lot of interest from the local aerospace industry. They told us that the Apollo people were retiring and that we needed to step up our space education. And we kind of started the whole astronautics program then, actually informally. And then in the early 2000s, we got it going as a regular department. We started our rocket lab at that time. So we've been doing this a while now, and uh, I don't have a big research group because I'm partly an administrator, but I do have two PhD students. One project on astrodynamics and artificial intelligence, where we're trying to get small computers on small spacecraft to be able to, using artificial intelligence, understand how to do spacecraft navigation in a way that would normally take weeks of computing. And then my other project, I'm actually a research member at NASA JPL. I'm actually at JPL right now. You can't tell from the background, but um, so I'm part of the radio science group where they use radio waves to determine all kinds of things from groundwater on Earth to composition of atmospheres on other planets, for example. So
Great.
that's my intro.
Thanks, Dan. We'll move it over to Professor David Barnhart. David.
Hey, everybody. Thanks very much for joining. We're excited to have everybody. Um, I am actually a research professor, so I do some teaching, but most of the time I'm supposed to be going off and creating things, breaking things, blowing things up. No, just kidding. Actually creating new things. So that's what research is all about. Um, I've also created and founded something called the Space Engineering Research Center. That's actually a joint activity between the Department of Astronautical Engineering and an off-campus institute called the Information Science Institute. So that's where I'm at today, even though I've got some labs on campus as well. The cool thing is that we, as the name implies, and as the department is driving, we have a very eclectic, sort of diverse kinds of projects in space engineering. Our group was the one that actually built and launched the very first satellites in USC's history. We have a clean room that we have students working in. We actually have our fourth satellite that's being worked on as we speak right now. We also were lucky enough to get the very first payload up into the International Space Station, which actually it still is there. Did a bunch of experiments with a little flying robot device called Astrobee. You may hear more of that from Garrett here in a second. And I've got, at the moment, I have about 8 PhDs that are pursuing all kinds of different ideas in different project areas that we have, about 20 graduate students, master's students that support that. And then undergraduates as they can come in, mainly in the summertime. That's typically when it is. Everything we do is, if you look it up, we're under Pasteur's quadrant. You can sort of look it up. That would be an investigation for yourself of what it is. It's all about applied engineering. That's really what we do. It's not theory. We actually like to get our hands dirty, develop simulations and support. And we actually do a lot of work with industry, various companies, as well as NASA, DARPA, the DoD, et cetera, government agencies. So that's us. Awesome that you guys are joining. Really appreciate it.
Thank you very much. And without further ado, one of our faculty members that is truly out of this world. It's not your last space pun. Uh, Professor Garrett Reisman.
Wow. Thanks, Paul.
Sorry, I
Wow.
nailed it with the low hanging fruit there. Sorry.
Yeah. So let's see. My name is Garrett Reisman. I was born in New Jersey, and in elementary school, I was the vice president of our chess club. How far back do you want me to go, Paul? Should I speed this up a little bit?
Yeah, let's talk more about your mom and dad's relationship. Let's go there.
They had a very loving relationship, Paul. I eventually went to University of Pennsylvania, where I studied both mechanical engineering and business management, and I graduated from there. Went to Caltech, did graduate work and research in multi-phase fluid mechanics and mechanical engineering at Caltech. And then, long story short, I got selected by NASA back in 1998 to be an astronaut, and reported to Houston. And for 13 years, I worked as a NASA astronaut, flew two missions, both up to the space station. First one was on Space Shuttle Endeavour in let's see, that was mm, 2008, right? 2008 was the first one, and I spent 95 days aboard the space station, which was actually rather disappointing because if you stay for 100 days, you get a patch. So I was just 5 days short, and they're sticklers with the numbers down there at NASA, so they wouldn't give me the patch, which is very aggravating, but I got over it. And then I got selected to do another flight on Atlantis, went back up to the ISS. This was a short duration mission, about 12 days. So 12 plus 95 is more than 100, but they still won't give me the patch. They said it had to be in a row. So, but I did three different spacewalks during those two missions, did a bunch of robotics activities. I installed one of the new modules on the side of the space station, was a flight engineer on Atlantis during ascent, so I helped fly the vehicle, and just generally had a really good time. It was it was pretty awesome up there. So now, after that, in 2011, I decided to leave NASA and I came over to work at SpaceX, where I worked on all of our human spaceflight activities and commercial. Was in charge of the team that tried to win the contract for NASA's Commercial Crew Program, which was successful, to help us build the Crew Dragon spacecraft to take NASA astronauts back to the space station now that the space shuttle was out of commission, and left there after holding a variety of different roles. My most recent role at SpaceX was Director of Space Operations, and in 2018, I left SpaceX and came to USC. And at USC, I've been doing some research in the areas of human factors and artificial intelligence and the teamwork between a human and an AI agent. But mostly I've been teaching, and the subject I've been teaching is astronautical engineering, specifically human spaceflight. I thought about teaching medieval literature, but I figured that would be like too far out of my comfort zone. So I decided to stick with human spaceflight. And I have a number of different courses. I have two different intro courses for undergraduates, for graduate students, and I teach a graduate class in human factors for human spacecraft and a graduate class in the hazards of the space environment and life support systems and spacesuits. Yeah, so come on and sign up and come and take the classes. It's a lot of fun.
Absolutely. Great. Thank you so much, gentlemen. For all of our guests, I'm going to start the next about 15, 20 minutes or so asking some questions that will guide you through learning a little bit more about the discipline of astronautical engineering and the coursework, the curriculum, and everything we have here at the Viterbi School. And then as we wrap up those questions, I'm going to open up the Q&A to all of you so that you can actually start asking some questions of these faculty. We're not going to do it just yet. I'll let you know when we're going to open the Q&A, but if you have questions, you might want to start writing them down or thinking about them, and we'll open that up in just a little bit. So first thing, I think we'll start with Dan on this one, but everyone please feel free to jump in whenever you like. Let's ask the seemingly most simple question, but probably most challenging to answer. What is astronautical engineering, especially when there's so many different types of aeronautical, aerospace, different types of majors with versions of these types of words involved and things that sound similar. But what is astronautical engineering for all of our guests?
Okay, well, you can define it a couple of different ways. One way is kind of by the end product. we're the people who design spacecraft, autonomous spacecraft that may spend years in orbit or going to other planets. We also design, build, fly large rocket vehicles, the vehicles that take the spacecraft to space. From the point of view of the curriculum, we're closest to, as you might expect, mechanical and aerospace engineering. One way you can think about this is, first of all, mechanical engineers see the world kind of by physical stuff that moves as opposed to electrons or information, although those things are very important too. You can't do any engineered system without electronics or software. So we work closely with engineers all across the spectrum, and many of us are on the spectrum. So, oh, pardon me. Um, So you can think of aerospace engineering as mechanical engineering with an emphasis on flying vehicles, and you can think of astronautical engineering as mechanical engineering with an emphasis on things that go to space. So just for example, we don't worry so much about the atmosphere, whereas the atmosphere holds up aircraft. For us, the atmosphere just sort of gets in the way. So we go through it to get to space. Our vehicles, if they have engines on them, they don't inhale oxygen. They carry their oxygen with them, and they carry their fuel with them. Or alternatively, they take their power from solar cells and use it directly to accelerate fuel with, for example, ion engines. There's many ways of doing propulsion, some of which were developed a long time ago, but have only become kind of practical and heavily used in the last few years. So if you've read about, uh, you must have read a lot of news about space, starting with SpaceX, and there's all kinds of new, small to medium-sized space companies. If you see photographs of the Earth taken from space, you sometimes see the byline Planet Labs or Maxar. Those are new companies that do high-resolution imaging from space using pretty advanced optical techniques that are able to get past the fundamental limits of optical diffraction with very clever algorithms. There's just to put it very briefly, space is really hot right now. And in the space curriculum, you learn fundamentals of mechanical engineering, and you also learn about things having to do with space specifically, such as, for example, orbital mechanics, spacecraft attitude dynamics, spacecraft communication, rocket propulsion, spacecraft structures. Um, and all these things have their analogs in other kinds of engineering, except perhaps for orbital mechanics and attitude dynamics, because they take advantage of things that no one else has. When you're in space, you can be up there for years with no forces on you at all. You're acting under the influences of gravity. Furthermore, if you start to tumble, you don't stop tumbling because you hit the ground or because air slows you down. You just keep tumbling forever. So there's all kinds of math and physics and engineering that really applies only to space vehicles, and that's what you learn in astronautical engineering.
That's great. Anyone else want to jump in with any other perspectives on this, especially considering our high school audience? No one's ever taken an astronautical engineering class. I'm curious if
Yeah, Paula, if I could, I would say that, just want to emphasize how our department is so unique and unlike any, really in almost any other school. So there's a lot of aeronautical engineering departments. There's a lot of aero astro engineering departments. Obviously, tons of mechanical engineering departments. But the thing that's different about us is that we're, uniquely focused on the space part. So really, it's like you can think of astronautical engineering as space engineering, and as Dan just pointed out. And I like to say that we're all space all the time. That's that's what we're really and very few if you go to an aerospace engineering department or an aero astro department, you'll get a smattering of space, but kind
Oh,
of the place.
Garrett, you're
we lost you for a quick second there, Garrett.
Uh,
I think you're back now.
okay, how about now?
Yeah,
Okay.
you're good.
Right. So I'm just saying that if you're really into space, if that's what it's all about for you, then we're kind of the place to be.
All right. Very cool. Speaking of given that we have an audience of mostly high school students and they're thinking about what their college classes will look like, what will their curriculum look like? I know, Dan, you kind of touched on this with some of the words you were throwing out there. But they'll what will the classes be that they'll take? How will they what will they actually be doing? What will they be working on? Or if any of you want to jump in on classes that you've taught and what that actually means to what it's like to be in that class.
Um, well, I'll start out at least. The the curriculum starts with me and ends with Dave. And
Okay.
what I mean by that is the very first course that you take as an astronautical engineer is Astro 101, which I'm actually teaching right now in the fall semester.
Well,
And it's an introduction, it's called Introduction to Astronautics. And it not only is it an introduction to space and space engineering, it's an introduction to engineering in general, because most people don't know that much about engineering specifically when they come out of high school. Maybe the counselors tell you guys that you're good at math and science, so you should be engineers. But outside of like robotics and Lego Mindstorm and a few things like that, there isn't that much engineering in high school. You might have been part of a rocketry group. Um, we have a rocketry group too, by the way, but the rockets are way bigger. They're they they have enough thrust that they could lift up a Volkswagen, and when they explode, they throw chunks of burning propellant for hundreds of feet. It's really quite spectacular. So I'm sure you've heard all the propaganda about our rocket group. So getting back to the curriculum, in the first couple of years, you take basically mechanical engineering courses with a few, well, and of course your basic math and science, like all engineering has. And you take also a couple of astronautical engineering courses. There's my intro course, and then in the sophomore year, you take an Astro 280, which is an introduction to orbits and spacecraft systems. In the junior year, is when things get pretty heavy, both from the general engineering point of view and in the astro point of view, because in the general engineering, in the junior year, you take a thing called mech optronics, which is a big lab course, which really you have to think for yourself, you have to learn to communicate for yourself, you have to learn to work with the real world, to conduct experiments, to do all kinds of things that modern engineers know how to do. It's really that course, perhaps more than any other, that actually turns people into being engineers. And then during the same year, you take Astro 331, which is spacecraft system engineering, which is the one that plus the follow-on senior year course, the capstone design course, mission engineering, that's taught by Dave. Those two courses are, along with all your basic courses, the ones that really turn you into an astronautical engineer. And they pull in all the knowledge that you get in a number of other astro courses, which I haven't mentioned. You take a specialized course in rocket propulsion. You take the spacecraft systems course is a broad introduction to all the different kinds of things that happen on a spacecraft, as well as all the associated physics. And as I mentioned, there's a bunch of physics that's everyone has to know, but it's really much more directly applicable to spacecraft. So again, it's a mechanical engineering curriculum with a bunch of specialized space specific coursework. And there's room for some elective. You could, for example, take Garrett's course undergraduate course in human spaceflight as an elective. Um, if you have room in your curriculum, and you could even think about taking Dave's graduate elective in ground station communications, where you actually get to track spacecraft using a dish antenna that we have on the top of one of our tall buildings. So now another big piece of the curriculum, it's not the required part, but there's the outside part, the optional part, is extracurricular activities. And every Viterbi department has extracurriculars. And probably across Viterbi, maybe the two best known are our Rocket Propulsion Lab and the Design, Build, Fly in Aerospace and Mechanical Engineering. We have actually two. We have Rocket Lab and we have Liquid Propulsion Lab. Rocket Lab is mainly solid propelled rockets. Liquid Propulsion Lab is mainly liquid propelled, as you can tell by the name. But any of these undergraduate student groups, they're extremely good because they're hands-on. You learn how to do real stuff. You learn how to work in teams. You either participate in national competitions or you do something that's really on your own, like Rocket Lab and Liquid Lab. They do stuff that really most other collegiate groups don't do. So um, no other collegiate rocket competition even comes close to what our groups do. So they're really all by themselves. So so if you're going to be an engineering student here, in particular an astronautical engineer, I recommend that you, of course, pay attention to your coursework. Not enough to get a 4.0. That doesn't, that's good for being a grad student, but not actually for that much else. I'd recommend you work hard enough to get like a 3.4, 3.5, maybe a 3.6, but spend your time and intellectual capital also doing other things. The some hands-on student activities, plus all the other things that the USC campus has to offer, because it's a major campus with international speakers most days of the week. There's a tons of activities, backpacking groups, all kinds of things. I can't even, hundreds or thousands of clubs. I'm sure Paul's very good at letting you know about all those opportunities. Oh,
Thanks, Dan. Given that you teased this, I'm going to kind of see if we can tee up Dave here. The bookend, he talked about his 101 class. Can you talk about your mission engineering class?
Yeah, that's the intention is, as the name applies, a capstone design class is meant to be, in essence, the other end before you go out. So I always refer to the class that I teach is you really have one foot in the university and one outside. And the whole point is to try to get you prepared for going outside, graduating. But the whole point is you're supposed to take all of the knowledge that you've gotten from Dan's classes and the curriculum that you've taken up to that point, and put it all together. It is a teams class. Specifically, teams are formed the entire semester. It's just a project. That's all that happens. But you have to work together. And so again, what Dan talked about relative to getting prepared for that, hopefully you've gone through some of that, either extracurricular or in some of the other classes. But then it's meant to really showcase the skill sets from each of the disciplines that you've grown up with, but then it's applied to a particular new problem. Every single year, I provide new problems, whether they're contemporary, whether they're something different, but everything happens in the space domain. And that's the thing that sort of, gives you confidence and gives us confidence that we've actually done the job. We've enabled you and given you all the tools to be able to take that step outside and go work for industry and be captains of the next innovations.
Absolutely. Dave, I want to stay with you because I want to shift topics here a little bit away from the curriculum over to research. And I know that as a research professor, you're doing a lot of work here, and you mentioned a little bit at the beginning. Could you talk a little bit more about the research that you conduct and maybe some other things that are also going on in the department?
Yeah, no, I appreciate that. So to sort of tie back to suggestions about what you can do in high school in preparation of, there is no question that, as Dan talked about, getting some intellectual capital related to an experience, there are things outside. So as an example, at our research center, many of the students, as Dan indicated, have been focused in the mechanical side or structural side, but quite a bit of the work that we do is prototyping, and a lot of that work ends up happening to developing PCB boards using real-time operating systems like Arduinos, Raspberry Pis, things you can go literally buy today, and you can start figuring out how to program. A lot of the students have to learn how to program to work with analog devices or digital devices, and there's a lot of specifics that go into that. Because in essence, the prototypes we put together for systems that we're proposing to go into space are really microcosms of the kinds of things that you would have to do if you were in industry and you're actually going to put something into space. Now, we actually do build satellites. We build CubeSats so far. A lot of electronics to it besides the structure. The payloads use optical cameras. Again, you can go buy things like that. You have to learn how to actually manipulate data that comes from various sensors. All of that is a very visceral, sort of hands-on capability. Dan mentioned one of the cool research projects he's working with is the idea to imply artificial intelligence now to guidance, navigation, and control. Well, what is GNC, guidance, navigation, and control? You're sensing things in the environment flying around the orbits, and you're trying to take all that data in, and you have to do something with it. Do I turn left? Do I turn right? Do I slow down? Do I go speed up, et cetera? All of that is based upon sensing systems or physical systems that you're bringing in. So a lot of the work that we do really centers on prototyping. And like I said, we have a lunar lander research vehicle, a prototype research vehicle that uses a jet engine to lift itself off and fans to control it. That simulates different gravity environments. We're building satellites, so we have a class 100,000 clean room here. All the students that go in put on the bunny suits and go inside and do like you normally see on TV. They're responsible to put it all together. We've done a lot of work with air-bearing device, basically just a piece of float glass sitting on an optical bench, and then we make these float bots that blow air down and lift themselves off. Now, why would you do that? Well, you do that because you want to try to simulate the dynamics in space. You can't do it perfectly, but you can get a little bit close, and that's really cool because now we can demonstrate swarm behavior or multi-spacecraft behavior or even rendezvousing two things together. And that's where we've created the first project that went up to the ISS that's actually flying on a free-flying robot called Clingers. Was all about a new idea for rendezvous and proximity operation and a device to connect two things together. So yeah, we're a lot of sort of eclectic activities relative to the research we're doing.
Where does the name Clingers come from?
Yeah. So actually, hats off to a previous or a current USC researcher, Dr. Baruch Kashnevis, who did his patent on something called Cling. And basically, you'll kill me, but I forget exactly the acronym. But it's all about a genderless docking system that he created for robotics on the ground. And I called him up one day and say, "Hey, Baruch, we got this idea to take your Cling thing and put it in space. Can we do that?" And he's much older. He goes, "Yes. Yeah, sure, kid, you can do that. Go for it, right? Go do that." So we just added a bunch of eyes to it, basically some more sensors and put it in a box, and now we've got Clingers. So we added the sensor, so that's where it came from.
Awesome, thank you. Garrett, do you want to talk about your research that you're doing?
Sure. Well, the project I was working on just really came to an end as my PhD student defended his thesis and graduated. But we were working on looking at for deep space habitats. So when we're talking about sending astronauts to Mars or even further away, and you get these comm latencies in tens of minutes or longer, our current paradigm of how we do command and control and communication and operations with the ground won't work because with that kind of a delay, a time delay, you're going to ask a question and you're going to have to wait, a half an hour to get the answer back. So if it's like, should I cut the red wire or the blue wire? And you can't wait that long. You got a problem. So we
Diffusing a
realized
lot of
that,
bombs up there.
yeah, it's important. So we realized that probably the way we're going to go in the future with the advances being made currently in AI is some kind of mission control in a box, some kind of a smart agent that would use AI to replicate the support that we get when we're on the space station from mission control. But that raises some interesting questions, which is how are these astronauts going to interact with this machine as opposed to interacting with a human? And what makes for good teaming and makes for them to get along well and perform well as a team, and what is toxic to that teamwork. And we focused on one particular area that we called investment, which was the willingness of the human to spend their resources helping the machine. And that's obviously very important for the development of any AI. But if you think about AI that's your teammate on a space station around the rings of Saturn or something, then it's especially important. So we looked at that dynamic and tried to figure out, try to understand what makes for good investment and what situations kind of make for bad investment.
That's great. And Garrett, I want to stick with you for my next question here, but then of course others please jump in. Oftentimes students are curious about where this all leads, outcomes, what's going to happen after college, and given anecdotal or whatever you want to talk about, where do our graduates go on to? What do they do after their college years?
I'll speak about my particular area of our department, which is human spaceflight. I have a little niche, and in that niche, that's a cool thing, and it's one of the reasons I decided to come back to academia and start teaching these courses. Because if these courses were available, like spacesuits, say, or life support systems, And when I was in grad school, I would have taken them. I would have loved it. It would have been really fun and great, interesting topics, but it would have been purely theoretical or just in the classroom. There was very few opportunities back then to go out and get a job building spacesuits or building human carrying spacecraft. We had the space shuttle, the space station, but that was pretty much it. Nowadays, with the advent of commercial space, we have companies that you've heard of, like SpaceX, and obviously you've heard of Boeing, and you have the Dreamliner, you have the Dragon. But I have former students now that are working at SpaceX. They're working at Boeing on the Dreamliner. They're working at Blue Origin on their lunar lander. They're working at Axiom Space on their next generation spacesuits. They're working at VAST right here in Long Beach, where I also work as an advisor on my part-time, and making commercial space stations. So you have this whole massive industry that is growing every year, and there's so many opportunities, and our students are working, at least the students that take my courses are now working in all those places. And it's great because every time I go visit one of these places, I see some former student, and it's kind of like a little reunion. So it's fantastic.
That's great. Anyone else want to jump in on that, or did Garrett cover that well?
Yeah, no, I was gonna say there's sort of two really interesting things about what you can do as a graduated astronautical engineering. One, obviously, what Garrett talked about is the explosion of what really is happening in the commercial sector, which honestly is gonna last, I truly believe, at least a decade, if not more. The really cool thing is that there's finally technology that has opened up the space domain for space servicing. In the past, satellites have been put together. You do the best you could and you throw it up, and if it works, great. If not, oh well, right? Now that's going to completely change with the advent of now being able to do maintenance, repair, refuel, et cetera, in orbit, in addition to commercial stations, and all that's going to just really explode. So I believe you guys will have an amazing number of opportunities. The second thing is really interesting, and this sort of goes back to what Dan was saying about what's the core in the curriculum different with us. Astronautical engineering is one of those really interesting curriculums that, whether you know it or not, whether you realize it or not, when you leave, you will have an understanding of systems in a way that in many other curriculums you don't necessarily get. And a systems engineer or systems thinking, honestly, that means you can apply your degree and your aptitude to almost anything that you want to go out and do. And to me, that's what's really, really cool about what I think astronautical engineering brings.
Actually, I can give kind of an example of that. In there are, as you know, a bunch of companies trying to develop things like self-driving cars, and a bunch of our graduates have gone off to systems engineering positions in self-driving car companies. Why? Because the self-driving car companies are mainly kind of Silicon Valley types who are used to bringing things to market really quickly and without a lot of thought and without a lot of safety. And whereas in Aero and Astro, things have to be reliable because you spend millions of dollars putting something in space and you never get to bring it back in the shop and fix it. So it has to work. So we're really good at figuring out things in advance and figuring out problems and solving them before they crop up and making things that are actually going to work and be safe. And that's trickling over into other industry as well.
Yeah.
But that isn't the majority of our graduates. The majority of our graduates are SpaceX is one of the bigger employers. The other propulsion companies, Garrett mentioned Blue Origin, Virgin Galactic, companies like that. We have a number of our graduates at the various NASA centers. A number have started their own companies. There's some that are even getting to be fairly well known now. Ursa Major, Relativity Space, Violet Labs, all started by our alumni. And so it's kind of exciting because for a long time, space was dominated by military and very large scale commercial and government operations. Nowadays, it's been true since the 90s that investment in space is well over, or dollars in space is over half private space, but increasingly it's small to medium brand new companies that venture capitalists are putting their money behind. You didn't used to be able to find venture capitalists willing to put their money in space. Now they are. They're kind of, in some cases, lining up to do it. So it's really space so hot right now.
There's a joke in there somewhere about temperature in space. Um, this will be my last question, and as I'm asking my last question, I want to let all of our audience know that I've opened up the Q&A feature. And so at the bottom of your window towards Zoom, you should see a Q&A button. Go ahead and type your question into that Q&A. I'm going to come back to it in just a little bit. I'll also let you know that this is going to be a democratic process, and so we will answer the most upvoted questions. And so if you don't have a question, but you can vote the question up with a little thumbs up to see who is going to get their question answered first. And so whoever's going to have the most upvotes, that's who's going to get it. So go ahead and type your questions in, or look who else is asking questions, and upvote that in. So make sure you're continuously paying attention to that. And I'll come back to those questions in just a moment. My last question for you all before we get into this is open to anyone, is, engineering moves pretty fast. Things are changing day by day, if not week by week. What are you most excited about in the next 5 to 10 years related to this discipline of astronautical engineering?
I,
Go ahead, David.
okay. Yeah, sorry. uh, I would say it's the mergence of sort of what Garrett was exploring. It's the mergence of autonomy or levels of intelligence applied to the various either subsystems or in many cases the robotics that are being developed today, that's going to now be put into new space systems. What to me is fascinating is if we get to the point that we can now build things in space, it sort of completely reverses the thought process of all the things that we are pushing to launch and go through this very high G environment to go up there. So now, but if you build things in space, they may look completely different, or they may operate completely different, especially given we now are moving so quickly in terms of processing speed or some sort of autonomous intelligence or artificial intelligence that applied to that. So I think that to me is, what are you guys going to create in space that we haven't even imagined at this point? That's the thing that's really exciting.
The development that over the next 5 to 10 years that I'm most keenly following, and I think will be the most impactful, is SpaceX's Starship. So if it's an open question about whether or not this thing is going to work and achieve its design potential. If it does, it is truly revolutionary, not just because of the scale that it provides, but also because of the economics. We could drop the price of a kilogram to orbit by another order of magnitude beyond what we've already been able to do with the Falcon series of rockets. So the potential impacts are huge, and the whole industry is kind of waiting with bated breath and to see whether or not this works. Not only the rest of the industry, like at VAST, where we're working on commercial space stations, we have one space station we can build if Starship works, and then we have the other space station that we'll build if Starship doesn't work. And so there's a lot kind of hanging in the balance, and there's a lot hanging in the balance for NASA, for the Artemis program, because NASA's counting on Starship to be able to land humans on the moon again. So this one development project, and it's a big development project, billions and billions of dollars. The success or failure of this project, which is very much a undetermined outcome, will have a tremendous impact on where we go from here. So, and it's a fascinating story to watch. And if you've tuned into any of the webcasts, you can capture some of that excitement. But it's really hard. So I don't know how it's going to pan out. We'll see.
All right, gentlemen, thank you so much. We're going to dive into our questions, and I put in the chat, I should have mentioned, we're not going to discuss anything related to admission today or the application process. We have specific events that focus on that. So while we have our faculty here, it's much more about this particular discipline or this coursework or this particular kind of profession that we're going into. The most upvoted question that came right away was from Chase Holtzman. Chase, you win the prize for getting the first question. For students wanting to study space-related majors, is it better to do aerospace engineering or mechanical engineering with a focus on space? And I'm assuming he means astronautical engineering, because that's what we're here to talk about, which is neither aerospace nor mechanical engineering. But I think the broader question that Chase is getting at here is, I see astronautical, I see aerospace, I see mechanical, and I guess I'm going to rephrase the question: why is astronautical better? And of course, I'm going to ask the aerospace mechanical faculty a completely different question when I see them next week.
Well, the thing that I would say about that is it depends on how committed you are to wanting to work in the space industry. Um, I should say, by the way, that you shouldn't uh, if you do astronautical engineering, it doesn't mean that you're forced into that for the rest of your life. We've It's already kind of been discussed that the things that you learn in astro are do carry over into other industries, and you can work as a mechanical engineer if you want to with an astronautical engineering degree. And as far as that goes, employers don't care actually that much about what it says on your diploma. They care about what you can do. So when you interview, they're going to really want to not so much look at your transcript, but look at the things you've done as an undergrad. Um, but if you are uh, if you are worried about it, then um, I would say mechanical engineering is more general than astronautical engineering, and you can work in cars, you can work in all kinds of things, but you won't have the education that you would for the space industry that you would have, because in uh, in mechanical engineering you will take a bunch of terrestrial things, um, heat transfer, Stirling engines, things that don't really apply to space so much. We don't have as much, we don't do kinematics in the same way because we don't have machines with thousands of moving parts. So mechanical, even though the fundamentals are quite similar, the actual mechanical engineering major is uh, is not so applicable to the space industry. So I'm not going to say anything against mechanical engineering because SpaceX and all the other space companies employ tons of mechanical engineers along with tons of astronautical engineers. But it really kind of depends on what your interests are in.
Yeah, I will add to that. I know that students are often confused about what to do and thinking that sometimes choosing an undergraduate degree program is this kind of concrete pipeline to a very specific job, and that just isn't true. To expand a little bit further on Dan's point, SpaceX, as an example, is going to hire aerospace, astronautical, mechanical, electrical, computer scientists, industrial and systems engineers. They're going to be hiring practically everyone because what do they say? Rockets are hard. Rockets are complex systems upon systems. They're going to need all different types of engineers in order to move forward, and it's not just one type. So I think when you're looking at these degree programs, take a look at the different curricula plans that are on our website. See what types of classes you're going to take. All of them are hard. None of them are easy. The question is, when you're doing the hard work and having that late night, are you actually enjoying what you're learning? You're actually enjoying what it is you're getting out of that. And if it's related to space, well, that's what these classes are going to be. And if it's not, then go look at something else. That's what they're all for. And all of our students still work together. So as a reminder, you can keep asking questions. You can keep upvoting. There are a number of questions that don't have upvotes. So please take a look. You can push things up to the top if you wish to. The next question is from Nashia. I'm going to rephrase this one, Nashia, because this is not about admission. So I want to be clear when you say what you're looking for. We're not looking for anything in the admission process, but I think there is some good weight to your question, which is, are there any particular things that make a certain student thrive in astronautical engineering? I don't know if there is, but I'm curious what you all think, or if that's just something relative to just doing well, in engineering.
As far as skills and aptitudes, I don't know of anything really space specific, except maybe the openness to work in all kinds of different areas. If you heard what Dave said about what it takes to put real space systems, get them ready to be sent into orbit, uh, every every space system relies on electronics and software and materials and uh, as well as mechanical engineering and um, getting everything to integrate together and pass a vibration check so it doesn't destroy itself on the top of the rocket. And so uh, the willingness to come in and have a challenge and say, oh, I've got to learn a bunch of new stuff to figure out how to do this. But that's very appropriate for Astro. But I think I'd be selling the other majors short if I didn't say that that's important for the other majors as well.
Yeah.
I guess I would add to that, Paul. just a real passion for the topic. I think if the people that are successful in this field are people that have a real deep interest and a real passion for space exploration, whether that be human or not or robotic, whatever. When I was at NASA, the people that were working with me at NASA were all people that were there for the mission of exploration and for learning more about the space environment. And that's what made us tick. And all of us that were at SpaceX, we were there also for the mission of making human life multiplanetary. That's why we were there. We weren't there because SpaceX had a really good dental plan. I didn't join NASA because they have a nice daycare center. We were there for the mission, and I think that's what makes people. That's what's special about this particular field is you have such a compelling mission. And if that resonates with you, then yeah, this is the place for you. But if it doesn't resonate with you, if you're then you might want to try something else.
Actually, I'll say something about that. When you first come in as a Viterbi engineering student, whichever major that you've chosen, you take an introductory course. In our major, it's Astro 101. We have a sort of a 101 course in every major. And they're designed to be, even though they're major specific, they're designed to be kind of broadly interchangeable in the sense that in all of them, you learn about engineering, you learn about the major that you've chosen, and they're kind of motivational in the sense that if you come out the back end of that course and say, oh, this is great, I want more, then you pick the right major. Or if you take my course and you say, well, I really like this engineering stuff, but space is different than I thought. Oh, I don't like this at all. Then you can switch to some other major. Or in the extreme case, and this doesn't happen very often because we're pretty good now at matching engineering people with engineering students with the engineering major. If it happens that engineering itself is not something that you like, then you have time really early in your curriculum to switch to some non-engineering major. But as I say, that doesn't happen very often.
All right, great. The next question was from Nishita. Nishita was asking about Engineering Plus. Engineering Plus, Nishita, I'll answer this question, is for all engineering students at USC. It has nothing to do with one major or another. It's just the overall philosophy that we believe that students can take engineering courses plus other things across the university. So, of course, as an astronautical engineer, you can take courses across the university should you wish to do so at various levels of depth or breadth. And so the opportunities, if you want to take a dance class, you want to take a business class, or maybe you want to minor in something, you definitely can do those things. And that is not contingent on being one major or another. So that's definitely there for you should you wish to do so. And yes, thanks, Dave. I saw your message. We will get to that. Parker has a very detailed level of questions here. So if you all help educate Parker a little bit about astrodynamics. He's asking, what does the astrodynamics curriculum look like, as if there's a specific curriculum in astrodynamics? What kind of astrodynamics research opportunities are available at USC and undergraduates? And are there pathways for undergraduates to gain experience at JPL and astrodynamics? And I also want to add to this, I think astrodynamics is also sometimes referred to as orbital mechanics, if I'm not mistaken. And so can we help explain what this means to our audience and how that is part of the curriculum?
Astrodynamics does usually mean orbital mechanics. It can also mean attitude dynamics, that is, how a spacecraft turns to point in the direction that it wants to point with antennas and sensors, for example. So more generally, it means dynamics of objects in space. But yes, you're right. It's usually meant as almost as a synonym for orbital mechanics. And as an undergraduate, you study this in the beginnings of it in the freshman class. We look at numerical investigation. You learn how to integrate the equations of motion directly numerically, and we do some experiments, and you see how to get to the moon, for example. In 280, when you have some math under your belt, that's when we actually study astrodynamics kind of for real. And that's where you learn about all the different classes of maneuvers, how to do interplanetary trajectories, how to transition from a vertical launch trajectory to a horizontal orbital trajectory, to a hyperbolic escape, an Oberth maneuver that puts you on a Hohmann transfer to get to another planet, for example, or a fast transfer to another planet if you're carrying humans and want to get there quicker than the several years that humans want to spend getting to Mars. So yes, you study that directly in the first couple of astro courses, and then as part of the spacecraft systems design, you learn the interplay between what orbit you pick and what the spacecraft itself actually is. And all of engineering, but specifically spacecraft systems engineering, is a trade-off between different things. And one of the biggest trade-offs is what kind of spacecraft do you have? Is there one? Is there a swarm? Is it big? Is it small? And what kind of orbit you're in? Are you in a low Earth orbit, polar, equatorial, geostationary? What kind of medium, like the GPS spacecraft? So, as undergraduates, yes, you learn a fair amount of astrodynamics. The serious astrodynamics classes are at the graduate level, but you can take those as electives once you get close to graduation. We don't have a specific astrodynamics person on the faculty. We usually rely on outside advisors for people who want to do research. So, for example, there's a couple of people at JPL that have helped us out by being de facto research advisors in astrodynamics for a number of years, and we have a pretty close collaboration with JPL in that way. So
I can also add from a research standpoint, we actually do at least some levels of research relative to astrodynamics encapsulated in the what's called the rendezvous and proximity operations phase. So very specific. Once you get close, and then some of the equations of motion change, but we do a lot of simulation work. So if you actually took those courses, you would be part of creating the simulations, and then we actually translate that simulation into at least scale model levels that we can demonstrate, whether it's on the floating table, or if we're lucky enough, we actually get to demonstrate these things inside the International Space Station to actually fly around and validate that, you know, the work that was done actually works in 6 degrees of freedom. So there are subsets of it that we actually do work with.
There's a number of, the next question is from Saturn, and I'm not going to read it out loud, but as I'm scrolling through these questions, this seems to be the overwhelming question, and I'm not certain whether we've handled it well yet so far, but there's still discussion. Is aerospace better than astronautical? Is better than mechanical engineering? It just keeps coming up, and I don't know whether it was asked again. So I'm curious if we could put kind of a button on this, mechanical versus aerospace versus astronautical. I'll tell you all right now, my version of this: you can't pick a wrong choice. You pick the thing that sounds cool to you. And that sounds oversimplified, but you're not limited in your opportunities. You don't just live in space opportunities. You can't, there's another question about master's degree. Yes, you can go on and do different master's degrees in different areas down the road. It's much more about what it is you want to do. But is there anything else that we can kind of add to our conversation here related to aerospace, mechanical, astronautical, and also the fact that other schools have different named programs that sound similar?
Aero guys are generally passionate about aircraft. Space guys are generally passionate about rockets and spacecraft.
Yeah, it's as simple as that. You like planes, go aerospace. You like space, go astronautical.
If
Mechanical
you like
engineers,
cars, and things with gears, if you're a gearhead, go mechanical.
the more moving parts, the better. Then you go mechanical engineering.
I think just to echo what Paul, you just said, and Dan said before too, which is that you can't go wrong. So don't stress about this too much. It seems like there's a lot of anxiety about this choice. But the truth is that you could be an astronautical engineering student and still work on cars when you graduate. And you could be a mechanical engineer like I was throughout my undergrad and graduate career and end up living in space for 107 days. So, you know, there's no one correct path. And there are other differences between the departments. We have a relatively small department. And you know, the aeronautical and mechanical department at USC is a lot bigger. So if you like a big home or a small home, there's other factors that come into play. But I would just say find which department seems the most comfortable for you and go for it, and don't worry too much about it. Like you said, Paul, there's no right or wrong answer here.
And we'll let it end on that. I have one final note for all of you as students that will be applying for fall 2026. When you're thinking about putting that down as the major, you do have to choose a Viterbi school major as your first choice major on the application in order to be considered for the Viterbi school. When it comes down to it is what you want to pick, the Viterbi school major in astronautical, aerospace, mechanical, or other engineering degrees, they're all there as long as they're prepended with the letters VSE. As long as it's a VSE major, then you'll be seen by us. You're never locked into that major either. So what Dan mentioned before is that when you apply to that program, you'll be accepted to that program. We're going to have you take that intro class if you still want to. And that intro class asks you 2 main questions in addition to all the stuff that Dan talked about, which is, what the heck is this thing and do I like it? And if you don't, then you switch to the other one or vice versa. We have a very flexible program that hopefully cuts through some of the stress that I know you're all feeling. You can't go wrong. Just put down the thing that you want to study. If you want to learn more about our admission process and learn more about any of this, go to our admission website, viterbiadmission.usc.edu/events, or join us for another one of our upcoming faculty roundtable sessions over the next couple of weeks, including aerospace mechanical, that will be available also on that same page. But on behalf of all of our esteemed faculty here in the Astronautical Engineering Department, Professor Erwin, Professor Barnhart, and Professor Reisman, I do appreciate you taking the time to talk with our students. And if you missed any part of this, the recording will be up on YouTube within about a day or so. So thank you so much, everybody. Have a great rest of your evening. Bye-bye.
All right.